Hi, my name is Mitch Adler, and this summer I worked with Professor Edwin Olson of the April Robotics Lab in developing an embedded computer vision appliance. The problem we chose to approach is that small robots, just like all robots, need a way to recognize each other. Knowing where other robots are allows each robot to understand their position better because they can use the data not only that they collect, but all robots collect, and also to better plan their path through the world. Small robots also cannot support current solutions to this problem due to their size. Current solutions would include April tags, also developed at our lab. However, because these tags would have to be shrunk down, they would no longer be able to be detected at the range required. A solution to this problem would be placing LEDs that blink code on each robot and having also all robots enabled to detect these blinking codes, similar to Morse code, which would correspond to numbers which would ID different robots uniquely. There are a few constraints that are inherent in this problem. First, there are computational constraints. Computer vision algorithms are quite computationally expensive. And also, robots must do much more than computer vision. They have different things like path planning, which we mentioned before, and other data detection. Also, there are physical and monetary constraints. First, the robots must be compact. Any hardware added plus the computational hardware must be compact and small due to the size of the robot. They also must be inexpensive. Also, we chose to, as a solution to our problem, we chose to offload the vision work to an embedded platform. We chose the Panda board as this platform. The Panda board, developed by Texas Instruments in collaboration with the open source community, is a very powerful and small computer containing a dual-core ARM Cortex-A9 with a Power STX GPU, among other impressive hardware features. It has a small form factor and is quite inexpensive at $174. You can see a picture of exactly what a Panda board looks like and its components at the bottom of this slide. Using a Panda board, we implemented an LED tracker. This enabled small robots to recognize each other and did so by detecting LEDs using a difference of Gaussians approach. We also accelerated these algorithms using the Panda board's graphics processing unit, using OpenGL ES 2.0, which allowed the Panda board C code to communicate with the graphics processing unit, and GLSL, which was the actual code executed on the GPU. The features we detected from the images were a specific subset of scale invariant feature transform features. We detected these features by blurring the image using Gaussian kernels, then taking the difference between the blurred images and finding points that are maxima. This algorithm is inherently parallel and was well suited, therefore, for GPU acceleration. As you can see below, an original image was blurred 4 times using a Gaussian finite impulse response filter. First, a 9x9 kernel was used to produce the first image on the top left. This image is slightly blurrier than the original image. As you then circle clockwise through the images, you go to an 18x18 kernel, 27x27 kernel, and 36x36 kernel. Each of these images, you can see, becomes increasingly blurry. These images were then subtracted from one another, pixel by pixel, to produce the 3 images you see below, which detect blobs of color and edges of objects. As you can see, when maxima from these images are detected, the blob of the LED, which is circled in blue, was detected as a small white dot on the image on the right, at the corresponding coordinates also in blue. As you can see, from our results, we successfully detected an LED at 7.2 frames per second. This is slightly slower than we would ideally want, and at a resolution slightly lower than we would want. However, both of these parameters can be improved through design optimizations in the code and the way certain algorithms are run. Also, we detected a significant number of false positives with few to no false negatives. This is by design because later processing can remove the false positives, while if one fails to detect a point of interest, that can never be recovered. Thank you, and I appreciate your time.